Well, here's problem 67. Here we have an inclined plane with a pulley and two masses connected by a rope. Um, Suppose the coefficient of kinetic friction between mass A and the plane is 0.15, and that MA and MB are equal, 2.7 kilograms, and MB moves down. Determine the magnitude of the acceleration of MA and MB given an angle of 34 degrees above the horizontal. So they've already told us that the system's accelerating. So that's Newton's first law. Check that box. And then applying Newton's second law, the sum of the forces equals ma. Now what we need to do is label the diagram and then add up all the forces along the line of action using the Watt-Lowe method. So let's get started. Here we have a force acting on MB. It's pointing toward the center of the Earth, and that's the weight of the box. And then we have a force up due to tension. And then there's also another force of tension. Those are opposite but equal forces. And then we have the friction force, which acts opposite the motion. You understand that MA is going up the plane, so the friction is going to act opposite down the plane. We also need to take into account the gravitational force. And what we have here is a component of mg acting down the inclined plane. All right, so let's label those forces. This is Fg sub A, and that's equal to m sub A g sine theta. The friction force is F of F is equal to mu k m A sub g sine theta. Okay. And then we have the tension up, which is T sub A, and then up to the right, and up to the left. Then we have the tension on B, and then we have the vector that represents the weight of B, so M sub BG. Okay, I'm going to switch color here to blue, and we're going to add up all the forces along the line of action, set it to equal the mass of the system times the acceleration of the system. So let's establish the line of action and the direction in which we're going to add up these forces or inspect the forces. Well, let's go in the direction of the acceleration as suggested by one of your classmates. So I'm going to go up the ramp, over the pulley, and down. So that will be the direction of adding the forces. And that's also in the direction of the acceleration. Again, acceleration is up the ramp, and the acceleration is down for m sub b. So that'll be our convention. All right. Sum of the forces equals ma. And they are, imagine that stick figure inspecting the forces. So the first force we come to is minus m a g sine theta plus, and I say plus because the next force is negative F. So we're adding forces, which is giving me the sign. So plus negative mu sub k m a g cosine theta. Okay. The next force we come to is positive the tension on B, and then up and over the pulley and down we have minus T sub A plus, on the way down, plus M sub BG. And that equals the mass of the system times the acceleration of the system. All right. And that is MA plus MB quantity times A. All right. TA and TB cancel. So we're just going to eliminate those from the summation. Again, I want to just get in the habit of listing those tensions because in another chapter, a subsequent chapter, the tensions aren't equal if the pulley has rotational inertia associated with it. Okay, so here's the acceleration of the system. And in the numerator, consider this the net force. So these are all the forces combined, and that net force, for the most part, when divided by the mass system, indicate the acceleration of the system. So we have minus MAG sine theta minus mu sub k MAG cosine theta. We're going to divide all that over the mass of the system. So there's your symbolic expression for the acceleration of the system. Okay? I'm going to let you plug in the numbers, and you have the solution also loaded to Canvas, so you can check the answer off that. Now, that answers part A. The answer part B, I'm going to slide myself over here. Here's part B. What smallest value of mu sub k will keep the system from accelerating? So that implies that the sum of the forces equals 0. So our state of motion is, in terms of the sum of the forces equals 0, is either at rest or moving at constant speed. But since the coefficient of kinetic friction is that smallest value, that's just the object's moving, or the system's moving at constant speed. That being said, the net force equals 0, or the net force is equal to, MA plus MBA, where A is equal to 0. So I'm not going to worry about this term over here. I'm not going to include this at all, but to say that we're just going to set the numerator of our expression to equal to 0 and solve for mu sub k. So we have m sub b g minus MAG sine theta. Okay, I'm just rewriting the numerator. Okay, minus mu sub k and BG cosine theta equals 0. So I'm going to solve for mu sub k. And again, I'm going to do a quick solve. I'm solving that expression algebraically for mu sub k. So in my head, just to let you know, we're going to add mu sub k MBG cosine theta both sides, and then divide both sides by MBG cosine theta. So this is what we have. M sub B G minus M sub A G sine theta divided by M sub B G cosine theta. So that's simply taking the numerator, setting equal to 0, and solving for mu sub k. So there's our algebraic expression, or symbolic expression, for the minimum smallest value of mu sub k, such that the system will not accelerate it. It'll simply move at a constant speed. Again, I'm going to let you substitute the values into that expression to determine the mu sub k, and then check that against the solution provided for you in Canvas. Have a nice evening.